Hello and welcome to the Electronics Lab. In this video, we're going to look at this op-amp circuit here, which is called a difference amplifier. As with other op-amp circuits that we have examined, we're going to analyze this circuit to look at the relationship between Vout and Vin1 and Vin2. And as I'm sure you can guess from the name, Vout will somehow be based on the difference between Vin2 and Vin1. And just like other op-amp circuits we've looked at, like the inverting amplifier, the non-inverting amplifier, summing amplifiers, the output of the difference amplifier is a function of the input voltages and the resistors, which in this case are R1, R2, R3, and R4. And in this video, we are going to figure out what exactly that function is. So to figure out this function, we will need to use some of our general electrical circuit analysis tools, along with the assumption that this is an ideal op-amp. So no current flows into the inverting or non-inverting terminals. And due to the negative feedback, the two input terminals of the op-amp are at the same voltage. Now there are a number of ways to figure out the relationships between the outputs, the inputs, and the resistors, and I think that one of the most straightforward in this situation is to use superposition and look separately at how Vin1 affects Vout and how Vin2 affects Vout. So basically what we're going to do is take this circuit and split it into two, one with Vin1 and one with Vin2. And then we'll analyze each separately and combine the results together to give us the overall effect of Vin1 and Vin2. Let's start with Vin2, or looking at the non-inverting half first. So basically, to apply superposition, we have shorted the Vin1 to ground. So now R1 is connected directly to ground. Now we can analyze this circuit like a regular non-inverting amplifier circuit, with the only difference being our difference amplifier has a voltage divider at the input to the non-inverting terminal, whereas the standard non-inverting amplifier just has Vin applied there. So for this half of the circuit, the output due to input 2 is going to be equal to the voltage here at the non-inverting terminal times 1 plus R2 over R1. This is the equation for the non-inverting amplifier. The only thing that we need to add is the equation for the voltage at the non-inverting terminal, which is going to be equal to Vin2 times R4 over R3 plus R4. Standard voltage divider equation, and that's multiplied by the 1 plus R2 over R1. Next, we can look at the inverting half of the difference amplifier. And to apply superposition here, we've gone and shorted Vin2 to ground, so R3 is connected directly to ground. And since there is no current through R3 or R4, this circuit is the same as if the non-inverting terminal was connected directly to ground. And this is a basic inverting amplifier circuit. So to calculate Vout from Vin1, it is your basic inverting amplifier equation. Now we can take these two halves of the circuit with the two equations that we've just figured out, and it gives us a Vout that's equal to the Vout due to Vin2 plus the Vout due to Vin1 to give us an equation that looks like this. So this equation for Vout seems like quite a handful, but in some special circumstances, it is much easier to deal with. First of all, if all of these resistors are the same value, just call that R. This greatly simplifies this equation. And this is truly a difference amplifier. The output is equal to the voltage at input 2 minus the voltage at input 1. Now what if R2 and R4 were equal to each other, and R1 and R3 were equal to each other? This also greatly simplifies the equation. And I'm going to rewrite this with a common denominator of R1. These two terms cancel out. So here we get a Vout that's equal to some gain R2 over R1 times the difference between input 2 minus input 1. So I've built the circuit over in LTSpice so we can look at a couple of these different cases. And so here's the circuit here. You can see input Vin2 is a sine wave with an amplitude of 2 volts and a frequency of 1000 hertz. And input Vin1 has an amplitude of 1 volt and also a frequency of 1000 hertz. Here's my op amp that I'm using, and it's a universal op amp or an ideal op amp from the library. And in this example, you can see R1, R2, R3, and R4 are all the same value. I am going to run a transient response for 2 milliseconds. This will give us a couple of cycles of the sine wave. And I've got an output load connected here of 220 ohms. It's an arbitrary value. It's just so that we can see the voltage across a load. So simulate. And now let's look at input 2. There's my 2 volt peak wave. Input 1 is a 1 volt peak wave. With all of my resistors the same value, the output should be Vn2 minus Vn1. So let's take a look at the output. And there it is, amplitude of 1 volt. Now if I change R2 to be a bigger value, let's go 5,000 ohms, and R4 to match it. Now we are looking at this case here. The output will be R2 over R1. 5K over 1K gives me 5 times the difference between input 2 and input 1. So that difference is 2 minus 1, and then it's going to have a gain of 5. So let's see what happens when I simulate this. There you can see input 2 is my 2 volt peak, input 1 is my 1 volt peak, and the output now has a 5 volt peak. Okay, let's look at one more example, this time with some arbitrary or different values for R1, R2, R3, and R4. You can see the values here. And here's my general equation for the output of this difference amplifier. And now if I plug these numbers into the equations, I get 3/5 of Vn2 minus 2 times Vn1 will be my output. And if I have 2 volts at Vn2 and 1 volt at Vn1, my output is going to be 3/5 of 2 minus 2 times 1, which gives me negative 0.8 volts. So this means my output will be 0.8 volt peak signal, but it's going to be 180 degrees out of phase with my 2 inputs. Now going back to LTSpice, you can see I've put the resistor values in for R1, R2, R3, and R4. Now if I go and simulate, and I bring up Vn2 is my 2 volt peak, Vn1 is my 1 volt peak, and my output is out of phase with those two with a peak of 0.8 volts, just like we calculated. So a difference op-amp circuit is one whose output is proportional in some way to the difference between the two inputs, and the proportion can be set with the resistors R1, R2, R3, and R4 in the circuit. I hope this has helped with your understanding of difference amplifiers. Now, since you made it all the way to the end of this video, you get an Easter egg of wisdom from Jack White. +1 and -1 equals 0? That's a defeatist attitude. I know it's counter to logic, but a good Zen koan anyway. Thanks so much for watching. See you in the next one.